Hi everyone. This video is going to be going over 3D solids, specifically these four that I've got up here. And these four are called the primitives because they're sort of the simple building blocks that you're going to be using in 3D software for all of your modeling and design work. So those are the cylinder, cube, sphere, and the cone. What we're going to be going over today is the volume and the surface area of these. Some of these I'm not going to be able to derive or kind of give you an explanation for why the volume is the way it is, or the surface area has that particular formula. So for those, and I'll highlight them in the video there, you will not have to memorize those specific formulas. So, for example, the surface area of a sphere, we're going to need calculus in order to give that formula. So some of these you'll need to know how to find intuitively, and I'll go over that in the video. But some of them I will just provide for you on exam 4 and the final. So let's get into it. This is blender that I've made these in. I'm going to start off with the cube because that's sort of the easiest primitive to start working with. Cube has length, width, and height are all going to be the same dimension. So I'm going to give that just a measurement of A. So A is the length, width, and height. I'm going to use A and B for each of these primitives just to kind of keep things simple and to avoid confusion with what's the R, because when we get to the cone, those measurements are going to be a little hard to parse out because we'll have multiple radius values. Over here, I've got the 3D solid, that's A. And over here, I'm going to show the flattened out version of this on the left. So I can just pick any of these dimensions here, and that's going to be A as well. In terms of the volume, you've probably heard before that the volume of a rectangular prism like this is going to be the base, which is you can think of that as being this face here, is going to be A times A, and then you multiply that by the height of the object, which is also A. So length times width times height is going to be A times A times A, or the volume you can see over here on the right is going to be A cubed. The surface area for this is going to be well, we've got 1, 2, 3, 4, 5, 6 of these squares here, and each of them has a dimension of A times A. So A squared plus A squared, A squared, A squared, A squared, 6 times that surface area is going to be 6A squared. So that's for the cube. That would be an example of one that I could expect you to have memorized. All right, because we can picture what that cube looks like, and we know where the volume and the surface area come from. One that I'm not going to be able to do that with is the sphere. So you'll be provided with both of these formulas for volume and surface area. In order to flatten this one out, so I've made some attempt here to flatten this out, but if you picture taking an orange and trying to take that peel off of it and flattening it out, you're going to need to make a lot of tears, and getting it into one piece is going to be very difficult. There's a lot of different methods for doing it. You could sort of peel off some sections like an orange, along that axis there, but there's no really good way to make a nice flat surface from this. three-dimensional shape here. You can see this when we try to make a 2D map of the Earth. So we've got our globe, and when we try to make a 2D projection of that, a lot of things need to kind of get compressed or stretched out, which is what's happening over here as well. You've got, things near the equator tend to be a little bit smaller, and things like, Antarctica and North America end up getting stretched out. Greenland looks huge, right? So there's been some attempts to sort of correct that on there, but they're all going to have some kind of flaw to them on here. In any event, we can just take for granted that the volume of this, if I give a measurement from the center of this sphere to the edge here, I'm going to call that A. That's sort of the radius of our sphere. The volume of this is going to be 4/3 pi A cubed, and the surface area is just going to be 4 pi A squared. So those will be provided on a formula sheet, but in order to show you how we come around to those, we're going to need calculus, so we'll see if we get to that next semester. Maybe we can get a sense for how that formula came around. Another one that we can derive everything we need from it, so we know where those formulas come from, is the cylinder. So you can see here I've got some cuts that I made here in the red. That's how I flattened it out here. But I've got 2 circles, and then all the stuff on the side, which we call the lateral surface. I'm going to call this measurement here A. That's going to be my radius of that circle on the top, and height of that cylinder is going to be our little measurement B. So in terms of the volume of this, just like with the cube, we sort of had the base, A times A, multiplied by the height, which was also A. Here we've got a base of this circle with a radius A. So for this circle, our base is going to be pi A squared. All right, so here's pi A squared, and then we're going to multiply that by the height, which in this case is B. So we've got pi A squared times B is going to be our volume. For the surface area, we've got 3 pieces here. So I've got the circle on top. That's going to be pi A squared. Okay, so there's another. I'll just go ahead and label these both on the net. Here's A. Here's B. Like I said, pi A squared for this top one here, pi A squared for the bottom one. So that's in the formula. You can see I've got 2 pi A squared. So that accounts for the 2 circles that I've got here. And then this part here, I've got a rectangle. I know that the height of this is B, but if I want to think about what this measurement is, all right, this measurement across the top here, that's really the same. If I were to unfold this, that's going to be the same as this measurement all the way around here. Right? So if B is the height of this, and I'm sort of unwrapping this along here, this measurement is going to be the circumference of this top circle here. So the circumference of that top circle there is going to be 2. 2 pi times the radius, which in this case is a. So I've got 2 pi a along the top here and b. So that means that our cylinder is going to be, this rectangle here is going to be 2 pi a times b. Excuse me. So 2 times the pi a squared, that's going to give us the 2 circles. And then 2a pi times b is going to give us our lateral, or this stuff on the side. The cone is an interesting case, right? So that last one, I'm going to give a couple examples of this. Let's look at this cone here first of all. So we're going to have 2 pieces here, right? One of them is going to be this bottom part, the circle, and then the rest of it is going to be something that I'm going to have to cut up. So I've broken this up into a bunch of little triangle pieces along here. I can show you what those look like for a second there, right? Those triangle pieces. But when I cut this up, I want you to think about what this is going to look like. So here I've got my cut down here, and then I cut the circle out. And you can see that the shape that kind of happens when you unravel this top part here is I get sort of a sector of a circle here, right? So kind of a some portion of a circle. Now, this is going to be easy enough to figure out the area of that. So if I can give some names to these measurements here, the radius of the bottom down there, that's going to be A. But if I think about what this measurement here, so that's sort of the radius of our big circle that we're kind of looking at here, that's going to be this measurement right here. So I'm going to call that one B. So that's B, and this one's B here. Okay. This circle is going to be straightforward enough, all right, for finding the surface area. So for the surface area of that, this is going to be pi a squared for the circle part. And then for this part here, this is going to be a little bit tougher, but we can kind of employ a little trick here. We can take these individual segments and we can kind of arrange them like this in a sort of alternating pattern. I'll just do one more of these because I've got an example ready for this. All right. If I grab enough of these little segments here and line them up, I can sort of make a rectangle on there. So I've got one of these pre-made already, and I'm just going to show that really quick. But yeah, the idea is we can take all of those triangles and sort of line them up in a way that gives us a rectangle. So here's another cone on here. This one has less segments, as you can see. but still a for the radius, b for that long measurement there. The bottom part here, that's going to be our pi a squared. That still works. But now we've got this sort of rectangle that we can work with. So this would be a lot nicer if I had all 64 of those original segments kind of lined up to make this nice thing. But we can think of this as being a rectangle. So if this is A, this is going to be B here. So that circle is still pi a squared. This is going to be B. And then we can think about what this measurement is. So thinking about these lines here. So let's say I've got this line and this line here. Half of them, as I sort of go around the circle here, half of them are going to be up on the top here, and half of them are going to be on the bottom here. So if this whole thing, right, if all these segments in total add up to the circumference, which would be 2 pi a, right? So that's the circumference. That means that half of that circumference is going to be up top here, and half of that circumference is going to be on the bottom here, right? So we can call this measurement 1/2 of 2 pi a. Or if we want to simplify that, we can get rid of the 2's and say this measurement is B. This is just pi a. Okay. So our total surface area here is going to be B times pi a for this part. So pi AB plus the area for this one. So this is measuring the circumference, but the area for this one is going to be pi a squared. So pi a squared for the bottom plus pi AB for all of the sides here. This is an example of one that I'd like you to either memorize or kind of intuitively know how this works. In terms of the volume, that's one that we are going to need calculus to really get a good grasp on. There is an example video that I'm going to post in the description if you want to see the volume of this, but I'll kind of give you a very non-mathematical way to memorize this volume. So this will be provided to you, but if you think about this fitting inside of a cylinder here, this cone would fit inside of a cylinder. Might look something like this. So the volume of this cylinder would be pi a squared times b. And again, this is very not mathematical, but if you can kind of break this into 1, 2, 3 parts, the cone is going to be taking up 1/3 of that. So if you look at the volume for a cone, that's going to be 1/3 times pi a squared times b. Again, we'll need calculus for that, and if you want to see an actual breakdown of that, I do have a video link in the description for that. But yeah, just to summarize, the three that I would like you to, the three formulas that I'm going to provide for you are going to be the volume and surface area of the sphere, and also the volume of the cone. So everything else is kind of up to you to intuitively know how that works. A typical problem for this might be me giving you A and B, if it's relevant, and asking you to find the surface area and volume. Another thing I might ask, just to kind of test to see if you know what each of these pieces refer to, is maybe I'll say, instead of asking for just the total surface area of something, I'll ask for example, in this cone, maybe I want not the whole cone, but just the pieces on the side here. So I might say, hey, I want to model this hat, right? And I want the surface area of this hat, or lots of little things I can do just to make sure everybody's on the same page, right? I can take this and just say, hey, I want to make a paper cup. That's another way to ask it. How much surface area do I need for this paper cup? And I'll give you all the dimensions here and here. I could ask for something a little bit more complicated and say, rather than giving you this measurement B, maybe I give you the height of that cone and the radius. In that case, you're just using Pythagorean theorem to figure out that remaining piece. Another question I could ask you, just in a similar type of vein, I could ask for, just the sides of the cylinder. But anyway, you get the idea. When we meet in class next, I'll have a practice exam with kind of a multitude of examples of the kind of questions I might ask. But the first step is just kind of understanding all those formulas and seeing where A and B play into all of them. Okay, that's all I've got. So I will see you in class.